today we're going to look at Lesson 70, and Lesson 70 is talking about limits. It's property of limits and some special limits. A decent amount of these properties are pretty easy to grasp, and so we're going to kind of go through the 7 different properties proposed here, and then I'll show you some examples and then some special limits. So, example 1. If you look at example 1, it reads, the limit of the sum of 2 functions equals the sum of the limits of the individual functions. And the easiest way to do is to look at what it actually says right here. And you'll notice what it says is basically the limit of f of x plus g of x can be broken apart. And so if you have multiple pieces being added together, you can break them into individual limits. So the limit of f of x plus the limit of g of x. Okay. Example 2, or property 2, is the same thing as property 1, except that it is the limit of the difference of 2 functions equals the difference of the limits. So basically, as you see here, 2 limits being subtracted can be rewritten, 2 subtraction within a limit can be rewritten as 2 limits being subtracted. Same thing continues with number 3. Number 3 is product. The limit of the product equals the product of the limit. So again, you can split a product up into 2 limits, or you could also do the same of putting 2 limits together into one product. Example 4. Example 4 is, we've used this in terms of integrals, but this says the limit of the product of a constant and a function equals the product of the constant and the limit of the function. So if you notice right here, it's the limit of k times f of x. Well, we know k represents a constant, and so just like with an integral, that k can be pulled out front, and so it's k times the limit of f of x. Property 5 finishes our after the first 3, we had addition, subtraction, multiplication, and now we have division. The limit of the quotient of 2 functions equals the quotient of the limits, and of course this is given that the denominator does not equal 0. So the limit of f of x over g of x can be rewritten and reworked as the limit of f of x divided by the limit of g of x. Property 6. Okay, this is a different one. If the value of a function g is greater than or equal to the value of a second function f, and less than or equal to the value of a third function h, and if f of x and h of x both approach the same limit L as x approaches c, then g of x also approaches L as x approaches c. Now, you'll notice it says that this is called the sandwich theorem. You'll hear sandwich theorem. You will also hear it called the squeeze theorem. Both are appropriate names. Both names can be used in reference on the AP test. But what you'll notice over here, basically it's showing the value of g of x being between the value of f of x and h of x. Then if the value of g of x is between these two, and if both the outer ones, the f of x and h of x limits both equal L, then the inside one has to equal L as well. I'll explain with a graph in one of our backside examples to help you make more sense of that in a moment. And then property 7. If the limit of g of x equals L, and the limit of f of x equals f of L, and then you'll notice there is some function composition going on here. The limit of f of g of x equals f of the limit of g of x equals L. Now, to try and explain this a little bit better, again, this is one that's easier to look at an example, which we will do on the backside, but this first part right here that says the limit of g of x as x approaches a equals L, what that's saying is that just the inside function, so g of x, that limit must exist. And if it does exist, it has some value. So assuming that that does exist, then this next part here the limit of f of x as x approaches L equals f of L. That is just saying that the value of that limit must be in the domain of the outer function. So it has to work with the outer function, and that the outer function must be continuous at that part of the domain. If that is true, we can evaluate this limit of f of g of x by using composition of functions. So evaluating the inner limit and then plugging it into the outer function. And again, as I said, I will show you an example on the back side. So let's look at example 1. They give us two limits. Let the limit as x approaches 2 of f of x equal 3, and the limit as x approaches 2 of g of x equals 9. So basically they're giving me the limits for f of x and g of x, and it's asking us to find the limit as x approaches 2 of 2 times f of x plus pi times g of x. So we can apply a couple different properties from above. First of all, notice that there is addition. And so we can apply property 1 in that the limit of a sum equals the sum of the limits. So we can break that into two separate limits there. And then we can also use property 4. Notice there are some constants involved. So it's 2 times f of x and pi times g of x. And so we can use property 4 and pull those constants out. So I'm going to rewrite this. I'm going to pull my constant out. So it's 2 times the limit as x approaches 2 of f of x. And then I'm going to break this up. So plus, and now I'm going to do the second one. Again, I'm going to pull the constant out. So that constant is pi. And then it's times the limit as x approaches 2 of g of x. Now by doing that, the good news is I know all of those values. Okay, 2 is going to be 2. We were given the limit as x approaches 2 of f of x, and that value is 3. So we're going to have 2 times 3 plus, over here we have pi, and then the limit as x approaches 2 of g of x, we are provided that to be 9. So 2 times 3 plus pi times 9. Do some quick math there, and I have 6 plus 9 pi. And I would stop and leave my answer as such. Okay, so that's just an example of how you can use the sum, difference, product, quotient, and then the constant rules. So basically properties 1 through 5. Let's look at example 2. So example 2, I don't know that I would say it goes with a specific one of our properties, but it's just kind of thinking through limits. If the limit as x approaches a of f of x equals L, can we say that f of a exists? So I'm going to sketch a graph here. I'm just going to do a first quadrant thing. And I'm going to make up some graph that looks like such. And you will notice that yes, I purposely put a hole there. Okay. And so this curve that I drew is my function. Okay, just a random function I picked, f of x. And okay, it's stating as x approaches a. So that means a is an x value. And of course, by no coincidence, I'm going to put a directly under the hole, the open spot. It says as x approaches a, the limit of f of x equals L. So remember, when it equals a limit, that is the y value. And so that means I'm going to put L over here on the y-axis. And then, okay, so the limit as x approaches a. So as we travel this curve from both directions and we get closer to the x value of a, it equals L. So there's a graph explaining that. Can we say that f of a exists? So looking at this graph that I've shown right here, does f of a exist? And the way I have this drawn, no, f of a does not exist because that is an open value. Okay, in order for f of a to exist, there would have to be a closed value right there. Okay, or the other option is there would have to be a removed hole. Or is that the right wording? A removed value, okay? Where there is the thought that, okay, even though my basic curve is this f of x, that there could be a separate point that is part of it. So, can we say that f of a exists? And my response is going to be, no, we're not guaranteed that it exists. There's a chance it exists, but we're not guaranteed because a limit does not necessarily equal that value, it's just as it approaches that value. So I'm going to put a little bit of explanation here. I'm going to say no, and I'm going to, let's see, how do I want to say this? As x approaches a, the value of f of x approaches L. However, that does not guarantee that f of a equals L, or that f of a even exists. So, as x approaches a, the values of f of x approaches L. However, that does not guarantee that f of a equals L, or that f of a even exists. Okay, and I think I showed you some examples with the picture there. Okay, copy down what you need from there, pause it if you need to get more, and we're going to go on to the back page. On the back side, to me, this follows along with example 2 from the front that we just finished. Is the following statement true? Why or why not? If the limit as x approaches 3 of f of x equals L, then f of 3 equals L. So hopefully you're thinking about that. And if you think about comparing this to the front side, basically instead of talking about f of a, we're talking about f of 3 here. So if that limit as x approaches 3 equals L, does f of 3 equal L? And that's where we're going to say false. Again, f of x approaches L as x approaches 3. But that does not have to equal L when x equals 3. It could, but it doesn't have to. So I'm going to say false. F of x approaches L as x approaches 3. However, the function does not have to equal L when x equals 3. Okay. Moving on. Let's talk about example 4. If f is a function such that negative x squared is less than or equal to f of x is less than or equal to x squared for all values of x, what is the limit as x approaches 0 of f of x? So this is one where I'd like to draw a graph to help explain it. And I think a visual will help you greatly here. So what we're provided is that f of x is between negative x squared and positive x squared. So, remind me, what does positive x squared look like? Positive x squared is a right side up parabola with its vertex at 0, 0. What does negative x squared look like? Negative x squared is the upside down parabola. I'm going to redraw that. Upside down parabola with its vertex at 0, 0. And what do we know? We are provided that f of x is between those in values. So we don't know what f of x looks like, but we know at all times its values are between that of x squared and negative x squared. So with that in mind, again, I don't know what it looks like. I have no idea, but I do know one thing. Okay, that red dotted line is my made up f of x. Again, it's between the two functions. What I do know is one thing. Where does it have to pass through when it passes directly between those two parabolas? And it's going to have to pass through there at 0, 0, because both parabolas have vertexes at 0, 0, so it also has to pass through that point. Okay, so the question was, what is the limit as x approaches 0 of f of x? And based on looking at the pictures, that's going to have to equal 0 as well. This is an example of what was called the sandwich theorem or squeeze theorem on the other side. So, kind of my supporting details I can write is as the limit as x approaches 0 of x squared. Well, what does that equal? As x squared as x approaches 0, you're getting close to that vertex, so y is 0. And the other one also, the limit as x approaches 0 of negative x squared. Well, same thing. It goes to 0, 0, so that's going to equal 0. Then the limit as x approaches 0 of f of x, so that random red line I drew, is going to equal 0. And why does it equal 0? Because of the sandwich theorem. So I'm going to say by sandwich theorem. Okay, and again, you can use sandwich theorem or squeeze theorem. But right here is your overall answer, but it is good to be able to explain all of this, to write it out in a free response question and give your supporting details. So showing the limit of the upper function, the bottom function, and then also stating or mentioning sandwich or squeeze theorem. Okay? take a moment to get what you need down there, and then look at example 5. Example 5, if you notice, it's the limit as x approaches pi over 4 of the natural log of tangent x. So this is an example of property 7. And property 7 is the one where you have a composition of functions. We have tangent x inside of natural log. And there were 2 pieces on the front side. Basically, the inner function's limit must exist. And our inner function is tangent. And as x approaches pi over 4 of tangent, that will exist. And if that exists, it must be in the domain of the outer function. In other words, can we take the natural log of that? And so we will find this to work out as such. So rather than trying to do the limit of the natural log of tangent, make it a composition. So I'm going to move the natural log out front, say the natural log of the limit as x approaches pi over 4 of tangent x. And so, first of all, of course, as any math problem, we work on the inside. And the limit as x approaches pi over 4 of tangent x. Well, first of all, if you visualize a tangent graph, it's just those, almost looks like a cubic curve repeated, right? And if you think about our chart, tangent of pi over 4, when you plug it in, tangent of pi over 4 is 1. Okay, and again, think of the graph and the fact that it's a continuous curve, so it would be approaching 1 from both sides. Well, now, by taking that inner limit, we have now simplified this problem to the natural log of 1. And what do we know about the natural log of 1? It is 0. And so that's just a good way to simplify those problems. Okay. Real quick, I'm just going to, you guys can pull these up and graph these on your calculator if you want more specific details. The limits are already here. I'm just going to kind of draw the graph to kind of just support the answer. So the limit as x approaches 0 of 1 over x, and it says it's undefined. So what does the graph 1 over x look like? That is our reciprocal graph, where it has a hyperbola in quadrant 1 and a hyperbola in quadrant 3. Looks something like this. And the claim is that this limit is undefined because as x approaches 0, keep in mind a limit has to be the same from both sides. So as x approaches 0 from the left, it's going down. As x approaches 0 from the right, it's going up. And when it goes 2 different directions, it's undefined. Okay, second graph, the limit as x approaches 0 of 1 over x squared. Well, if you recall what 1 over x squared does, it takes the previous graph and squaring something will make it positive. So instead of it having curves in quadrant 1 and 3, they are now in quadrant 1 and 2. And these are good graphs to just be familiar with, to be able to have a visual without graphing them on the calculator. And so in this case, as x approaches 0, the limit is equal to positive infinity, because as we approach 0 from the left and from the right, both graphs are going up to infinity. Okay, example 3. What happens when we put a negative in front of that graph? The limit as x approaches 0 of negative 1 over x squared. Well, keep in mind a negative is going to reflect the graph, and so this graph is going to now be all negative. And so now my hyperbolas are down in quadrants 3 and 4. And this time it's as x approaches 0. So as we approach from the left and the right, both pieces of the graph are going down. And so this is negative infinity. Okay. Fourth graph. This is a special graph, and I do see this one come up on occasion. The limit as x approaches 0 of absolute value of x over regular x. And if you graph that on your calculator, you will see that it is horizontal lines. Now, it's a broken horizontal line though. In the left of the y-axis, it's a horizontal line at -1, and there's a hole there on the y-axis. Past the y-axis, this value is up at +1. Again, it's a hole there, and then the line goes to the right. So if we're talking about as x approaches 0, well, from the right, it's approaching a value of 1. From the left, it's approaching a value of -1, and so we will say that this limit does not exist. Example 5 looks at the same graph. The limit as x approaches 0 from the positive side only. So if I redraw that same graph, you will notice that as we approach 0 from the positive side, we're going on that upper horizontal line, and that is a y value of 1. And one last one. The limit as x approaches 0 of sine of 1 over x. Now, keep in mind, if you graph this on your calculator, which it is an interesting one to graph and look at on your calculator, make sure you're in radians because it is a trig function. And I'm not even sure I can do this one justice in drawing. Off to infinities, it's running along the axis. As it gets closer to the y-axis, it does some up and down curvy stuff. And again, I know I'm not doing that justice at all, but if you notice on the left side, I have that graph going to a negative y value. On the right side, I have it going to a positive y value. Those are not connected. One is negative and one is positive. So this limit as x approaches 0 does not exist because they are not approaching the same piece. Okay? So hopefully this lesson 70 was a little bit easier to understand in a video than 71 would have been when we did the volume. So, and you also should have some time to work on homework now. And I will see you Monday. Have a good weekend.